Beer-Lambert law. And we sort of derived what it's all about. It basically allows you to calculate calculations, and this law really is the absorption in a spectrophotometer that you can easily measure equals the concentration of the solution times the wavelength times the path length and times the extinction coefficient or extinction factor. So this is absorption of the light or absorbance. This is the concentration. This here is the path length. And we usually have 1 centimeter or sometimes 3 centimeter cuvettes. And this guy here, that is the extinction coefficient or extinction factor. Coefficient or extinction factor. Now, absorbance, you quite frequently also see it's called extinction. That's why there's this E. Extinction. Or sometimes people also call it optical density. Optical density, or OD. I just want to throw that in so that you're not completely thrown if you see things like that. It just means all the same stuff. We said that the Beer-Lambert law, does it in any way contain the wavelength at which we measure? If you look at this law, does it contain the wavelength at which we measure our concentration? Do you see wavelength anywhere in there? Well, that's the wavelength of the light that we use. No? That's absolutely crucial that you remember that. The Beer-Lambert law does not contain any kind of wavelength of the light. The wavelength is sort of hidden in this epsilon here because for each substance and each wavelength there is a different extinction coefficient. But it's sort of hidden in there. You don't have to do anything with the wavelengths. And I say that because I don't know whether I should call it entertainment or shock and horror. But very often you give students a nice question. You think it's a nice question. You say, a substance has an extinction coefficient at 420 nanometer of such and such and such, and the absorbance is 0.3. Calculate the concentration. A lot of even final year students say, oh, yeah, I remember. That Klapper that told us Beer-Lambert law, yes. So I just multiply the wavelength, 420 nanometers, by God knows what. And I go, oh, where did I go wrong? Wavelength, no. There is no wavelength in Beer-Lambert law, right? There's no wavelength in there. Do never ever multiply or divide by the wavelengths. It's a criminal act. Right? You will be persecuted for that. So, wavelength is taboo. Right? It's forbidden. Okay. And you can look up these extinction coefficients in books and so on. But what if you do not have an extinction coefficient? You are basically completely... Thank you, I didn't say that. Right? You can't do anything. Unless you are very, very clever. And what you can do in such a case is if you want to determine an unknown concentration, what you do actually is you make what is called a standard curve. We spell that with an E at the end. A standard curve. And you probably have heard about that in the previous session. Yeah? Now this is exactly the Beer-Lambert law, but without the epsilon in it. And all you need to do really is you make known concentrations, you measure the absorbance, and actually what you can do is you can calculate your epsilon from it. If you want to. You don't have to do it. So what you basically do is you have several containers, and let's assume we want to measure the concentration of a compound. So in your first container there will be the concentration of 0. There will be no thing that you want to measure in it. That's your zero control, or it's also called the blank. And then you increase the concentration. So I just do it 1, 5, 10, 15, 30. Whatever this is. Say millimolar or milligram per milliliter. So that is the concentration. And all you need to do now is really you measure your absorbance for each of these things. With one exception. You don't measure an absorbance for the first one. You don't measure the absorbance for the blank. What do you do with the blank? You calibrate the spectrophotometer. So you put the blank into the spectrophotometer and you say, this should be my 0. So you can press a calibration button on the spectrophotometer with the blank in, and the spectrophotometer should ideally show 0.000. So this one gives you 0.000, ideally. And then you measure all the others. So let's say here we get 0.01, 0.05, 0.1, 0.15, 0.3. That's in a very ideal world. It will never look like that, I can promise you that. But it doesn't matter. And with this, you can calculate a very nice standard curve. So what do? Well, you just simply take some graph paper. Let me see if I find graph paper. Ha! How cool is that? You draw your axes. And one of the biggest problems that lots and lots of students have is they get so overwhelmed with the beauty of the graph paper and their axes that they say, wow, it's so beautiful. You know, I don't need to do anything. Actually, I would like to know what these axes represent. It would be nice to know what these axes show. So, a graph without proper labeling is just, you can use that as toilet paper. It's a bit hard. You might enjoy it when you have piles. Sorry. So, what do we plot on the x-axis? On the x-axis, we always plot the things that we change. On the x-axis, the variable or just stuff we experimentally change. So, what did we change in our experiment? We changed the concentration of our compound. So, we would say concentration of BSA, of sugar, of God knows what. And we also, absolutely essential, we need to know what units this is. Yeah? So, concentration, and in our case we said this would be in millimolar. If there's no unit, I don't have a clue what it means. Forget it. On the y-axis, we plot what we measure. So here, stuff we measure. In this case, we measure the absorbance absorbance. What is the unit for absorbance? Sorry? There is no unit. Okay. Absorbance. What you can do actually to show that you understand it, you just say no unit. Yeah? That indicates, it's not just because you forgot it. It is actually, you know that there is no unit. And now what we can do is we can just simply put the data in. So, how do we go about doing something like that? I know lots of people have done graphs, but sometimes I see still rather interesting stuff from students. So the easiest way is to say, okay, fine, I have here my equidistant things. So I want to have my last number, that should be the largest. So here I've got, let's say, here 5, 10, 15, 20, 25, 30. Well, the way I've drawn it, let's do that 40 here. Let's do that 50. Yeah? So I would go 5, 10, 15, 20, 25, 30. I would probably in my graph go up to here. And a good graph design, that's quite important. What I sometimes see is people having this massive graph paper, and they draw the graph here. And I go, wow, I go blind. Or they start with a graph and then find out, oh, 10, 20, 30, 50. Oh, it doesn't matter, I can do that on the bench. Yeah, you can do that, but then you have to submit the bench. It's a bit inconvenient, right? So plan your graph well. And the same for the y-axis. So let's say here we have 0.1, 0.2, 0.3, and so on and so forth. And then you just simply draw your graph. So here we would probably go up to this point. We have this point. And that would be your graph. Yeah? Pretty straightforward. You might have a point here. We also have a point here. Wonderful. So, this is my standard graph with known concentrations. And if I now want to know what my unknown concentration is, I go back to here and I say, okay, I do exactly the same way as I have done my standard concentrations, and I do that with my unknown concentration. So that's the unknown. And I measure that, and let's say I measure 0.2 for that. Yeah? So all I need to do is now, with my standard curve, I say, okay, my unknown concentration gives me an absorbance, which is 0.2, which is this one here. So all I need to do is go here from 0.2 to where this horizontal line hits my standard curve. And from there, I go down and measure the corresponding concentration, which in this case would be 20 millimolar. And that is the concentration of my unknown curve sample. Yeah? Pretty straightforward. So that is basically what you have to do tomorrow in your assessed practicals. You make a standard curve, you measure your unknown concentration, the absorbance, and you try to read from your standard curve what the concentration is. So far, so good. Does that make sense? Yeah. Pretty simple and straightforward. At a concentration of 0, we blank. So, concentration of 0 should give us 0. So, concentration of 0 should give us absorbance of 0. So it would go through the origin. It should go through 0, 0. Okay? If it doesn't go through 0, then you might not have blanked it. You might have forgotten to blank it. Yeah? Could happen. Happens to the best. So, what could you do? You forgot, you are halfway through your measurement, you are here, and then your lab partner says, have you zeroed it? Good. No, I forgot. And your lab partner is going to be absolutely mad at you. So what do you say? What do you say to your lab partner? What a worry, huh? What would you say to your lab partner when they say, I forgot? Start again. Okay, I say, Hakuna Matata. Which means, no worries, exactly. Because what you can do is, your line would still be a straight line, wouldn't it? Even if you forget to zero. It wouldn't just, it just doesn't start at the bottom. It might start somewhere here. Yeah? But it's still a straight line. So how do we get from the blue line to the red line? Well, we just subtract from each data point the blank. Yeah? So if you blank, if you then blank it, and if your blank is, say, 0.01, you just subtract 0.01 from each of these data points here, and you are back to your normal red line. Simples. And if you've done your homework, with the spectrophotometry homework, there was exactly a question about that. Your blank shows 0.01. Calculate your concentration. All you need to do is, okay, my absorbance of the unknown was 0.3, I think. 0.3. And now I just simply subtract my blank from it. So minus 0.01. I get 0.29. And I just simply calculate further with that. Very simple. Yeah? So you don't have to repeat everything, although it's good if you repeat it and you still get the same stuff. That's quite reassuring. Another thing, just for your entertainment, what I sometimes see is people using very interesting axes. So, absorbance, and they have something like that in there. 0, 10, 100, 200, 800, something along the line of that. I shouldn't say along the line because that is absolutely horrible. So first of all, it usually takes me a while to figure out what this scribble is. What people usually try to indicate with that is that the axis is sort of interrupted at that point. So here is 0. Axis is interrupted at that point. No. an axis is never, ever interrupted by any means. An axis is either full drawn through, or it's not present. If an axis is not present, there's no graph. But, never ever do something like that. This is... What else do you notice? The scale is completely wrong. The difference from 10 to 100, which is 90, is the same as from 100 to 200, which is 100. It's the same from 200 to 800, which is 600. So it is not proportional. And you get fantastic results from that. What you usually get, it looks like a cross-section through the Himalayas. Yeah? Something like that. And then people say, oh, it didn't give a linear, a straight line. Oh, I wonder why. I know, I tell you things that are absolutely trivial. But a few years ago, I had a student, and I asked him to make a standard curve and to measure some glutathione, that's a component in the cell. And that was a final year student in his final year project. And after 3 days, he returned to me and said, I don't know what I'm doing wrong. Here is my graph. 1, 2, 3, 4, 5. And my graph looks like that. Okay, let's sit down. This is bizarre. It shouldn't look like that. It should be a straight line. Tell me, what have you done? Well, he says, I labeled my tubes. Okay. I put in the concentrations that you set. And then I measured the absorbance. That gives you this? Yeah? I've done it 5 times. It took me 2 hours to figure out what was wrong with that. And that was, I felt like Sherlock Holmes. What he put down on the x-axis was not the concentration of his standard substance. What he put down was the tube numbers. And you think, did I really teach you? I mean, where have you been the last 3 years? Yeah? So, no, it has to be the concentration, not the tube numbers. Or, the phone number of your girlfriend or something like that. Concentration. Okay? So this is what you have to do tomorrow. Not the tube numbers, but the concentration. And the straighter your line, the better it is. Can you do it? Go in peace.